problems. We're going to try to go over 3 problems today. We'll see how far we get. It generally should take me longer to do them on the board versus you guys doing them, because, you know, I like to get you guys involved. I'm not just going to, like, solve stuff like we're in a hurry. But we'll see, you know, based on the timing of everything. The types of problems I'm putting up are not that dissimilar from ones you're going to be getting, but they're dissimilar enough that it's not like I just changed numbers or anything like that. But generally, I think these are a fair example of the types of problems to get that you're going to get on this test. And these are actually from a test from 2006, I believe. Okay, so the first problem is going to be worth 30 points. And it reads, and I'll put critical things up here, but, you know, I'm not going to write down every word. So the gas phase decomposition of nitrogen pentoxide, which is that's nitrogen pentoxide, occurs by the following mechanism. So there's my first step. And sorry, my spacing's not great, but out here I'm just putting the step numbers. They're not part of the reaction. Okay, and the rest of the problem reads, the rate coefficients are defined with respect to a reactant species. So out here, I also have K1, K-1, K2, K3. The concentrations of the intermediates NO and NO3 remain small relative to the concentrations of reactants and products. So just briefly, NO and NO3 remain small. And notice that the first reaction is kind of written twice, both the forward and reverse. Make sure it does not throw you off if instead of writing it this way, I write it like that. Okay? If you see the double arrow, you know that you have to account for the reverse reaction. Okay, so part A says derive an equation for the rate of nitrogen pentoxide expressed only in terms of rate coefficients and concentrations of stable molecules. So what do I do? PSSA on NO and NO3. Is that where I want to start? No. So what rate is it asking me for? It actually says decomposition. I think I mentioned that. So I can write out the negative rate of N2O5. And so what is that equal to? R1, not minus R1. I'm writing the rate of consumption. This is already written as the rate of consumption. Minus the reverse reaction. That is true, because over here I'm producing it. Does N2O5 show up in any of my other reactions? Yes. So I also, again, is it being consumed or produced in that reaction? So I also need to add in a plus because it's being consumed and because I wrote the rate of consumption. So plus R3. Any questions? I'm going to try not to look at the notes We'll see how well I do. So R1 is equal to what? K1 times the concentration of N2O5. And R minus 1 is equal to what? So have we made any assumptions as we write these out?
These are elementary.
Yeah, these are elementary steps. If you're given a list of mechanisms, that's usually safe. I look back at this problem statement, I actually don't see the word elementary anywhere. But without that assumption, you'd have been hard pressed to do anything. Okay, and then R3. And just recall that if you prefer it, you're allowed to use that notation, right? Makes everything a little bit bigger, easier to read for the grader, perhaps. All right, so if I sum those up and I put them up here, I just get K1, concentration of N2O5, minus K negative 1, concentration of NO2, concentration of NO3, plus K3, concentration of NO, concentration of N2O5. So, which species can I leave in my final form?
Anything but
Right, so the concentration of N2O5, that's okay. The concentration of NO2 is okay. And the concentration of O2 is okay. But I can't put in the concentration of NO or NO3. It says that in the problem statement, right? Because it says that you have to express it in terms of concentrations of stable species. And those intermediates are not stable. So what do I do to get rid of those intermediates?
PSSA.
All right, so let's start with the PSSA on NOs. So the change in the concentration of NO with respect to time is equal to what? 0. And what else is it equal to? So we got to look back at our elementary equations.
R2.
Which reactions?
R2. Yeah, R2.
Right. So it shows up, it's a product of reaction 2. So there's no, right, it's positive 1 coefficient. And then where else does it show up?
Minus R3.
Okay, so right away, I can see that R2 is equal to R3, right? And that's probably going to come in handy. But let's go ahead and take that and substitute in. What is R2? And what is that equal to? R3, which is what? Okay. So I can solve for NO, but I'm still going to have NO3 here. I got to get rid of that concentration term. If I look back at my original equation, I also have NO3 here. So what do I do to get rid of NO3?
PSSA.
Right. It's safe at this point to start erasing. So the change in concentration of NO3 with respect to time is also equal to 0. Ah, damn it, why did I erase that? All right, I need your help. Where do I make NO3? R1. Is that it? One at a time.
You consume it at R-1 and R2.
And I also consume it in R2?
Yeah.
Is that it?
Yeah.
Okay. So again, you could write, if you wanted to, right? You don't have to rearrange at this point. You can rearrange after you've substituted, but sometimes it's nice to see these patterns. Okay, so R1 is K1 times N2O5. And R minus 1 is K negative 1 times NO2 times NO3. We got to add to that K2. I don't think I've had that one yet. Yeah. NO2 Okay, so you see there's no NO here, right? There's no concentration of NO term. So this is a good place to actually start rearranging and solving things. So we get NO3 is equal to K1 N2O5 divided by K negative 1 times NO2 plus K2